Good evening. Welcome to Matinee Free Webinar. Today, we have a wonderful session on computer chips. Particularly, there is something related to India's mission. This talk is by Vice Admiral KANNAN sir. And this is his sixth talk. There are five very important, wonderful talks. Basically, one is new indigenous technology, 6 new indigenous technologies. Another one is melting Arctic ice, something related to India, and mineral security of, and it's a challenge for India, e-waste, and finally the hydrogen genset. Today, the 7th talk from respected Vice Admiral KANNAN sir. So on behalf of you all, I invite KANNAN sir, and KANNAN sir, you are welcome.
Okay, thank you. I would like to see once if you can select my video. But at the outset, let me thank Sabu for giving me another opportunity. Today's topic is very important, and I would like to share an experience with you before I start the presentation. I bought a car 8 months back. And when the car was delivered, they told me you're able to get only one key. The second key will be only manual and not have that remote control. So he also said, we have a chip shortage. And because the chips are not there, you will get your second key only after few months. Of course, I had to wait for 8 months before I got my second key, and I realized how so many customers, some of you may also have experienced this, so many customers are facing difficulty in getting complete set of their procurement items because of shortage of chips. There are problems. And chips are not only in the car. Chips are also there in your mobile phones, your washing machine, your refrigerator, microwave, and most of the domestic appliances which you use today have chips embedded in them, customized chips embedded in them by the manufacturing companies. The only thing is chips are imported in India. No chips are made in the country. And we'll talk more about it as we go along. So all the electronic equipment which you hear, which are being made in the country, be it be Bharat Electronics, be it be Tata's, be it be some other company, Mahindra's, all of them get their chips from abroad. Not a single chip is made in the country. So if you say electronic industry is contributing so much percentage to GDP, I'm talking electronic equipment production, which contributing so much percentage to the GDP, please reduce from that percentage the amount of imports which you have incurred for importing chips so that the equipment can be made in the country. You may be doing more than assembling and testing, but the fact is major components where the software sits or where the software is controlling, those chips are coming from abroad. So we're going to discuss this issue today. I have decided to make the presentation in 3 parts. First part is slightly technical. You'll have to bear with me. You need to understand what's the intricacy of a chip. So I will make it as simple as possible for all of you to understand. And the second part will be, why does India want to manufacture chips now after neglecting this industry for nearly 40 years? Why are they doing it now? There must be a reason. There must be some compulsion. So that's the second part. And the third part is, how is India going to do this commencement of semiconductor industry? That is the third part and the final part. So with this background, I will upload my presentation now. Okay, I'm sharing my presentation. Are you able to see it?
It's coming only, sir. You're not selected.
I have selected. I'm already sharing the, okay, I'll stop sharing it and once more
You
share screen, select. Able to see?
No, sir. You have to select the PowerPoint.
Oh, I have already opened and kept.
No. I can see the screen only. No. You just select
Okay,
this.
you.
Sir, ഒന്നുകൂടെ ഒന്ന് എടുത്തിട്ട് ആ PowerPoint ഒന്ന് select ചെയ്താൽ മാത്രം മതി. ഒന്നുകൂടെ share ചെയ്തു.
PowerPoint, I have already minimized and kept. I'll go for share screen. Now. Okay, I'm sorry. I made a mistake. My mistake. Okay, you're able to see the screen now?
Yes, it's okay.
Can I go to full mode?
Yes.
Okay, now you're able to see?
Not in full mode.
It's
Yes,
in full,
it's okay.
full mode. Okay.
Okay.
So I'm going to start my presentation now. Sorry for the glitch in the beginning. So let me say that there are many types of semiconductor components. There are capacitors, resistors, diodes, and integrated circuits called ICs, which are called chips. So we are going to talk only about the ICs today. The rest of the things, some of the items we are being made in the country in a very limited manner. Some R&D work is also going on. So we are going to speak on integrated circuits, which are called chips. Now, chips actually came in 1980s. They were actually a enhanced version of transistor, which came in 1960s. So when I did engineering along with Sri Kumar and Matthew, etc., when we did engineering, vacuum tubes were already on the way out, and chips transistor had come, but chip had not come. So people like me, I am an electronic engineer. We have grown in this technology along with growth in semiconductor industry and semiconductor applications. So this is the background of how the chips came in 1980. Now, as I mentioned to you, they replaced the vacuum tubes, which were bulky and power guzzling. Now, semiconductor material, many people say it's a half conductor. It can be made to be a conductor. It can be made to be an insulator also. So you can have two extremes of resistance to electrical flow. You can be a conductor like copper, iron, etc. Or you can be an insulator like rubber, glass. And semiconductor lies in between regarding its resistivity. But you can make the semiconductor a conductor, or it can be made to an insulator. That is the primary advantage of semiconductor. I will not go to the physics of it, but I will tell you the applications of that. So, as I told you, it can be made to flip and flop between conducting and insulation, just like 0 to 1 and 1 to 0. It can be made to do that. Or just like opening a gate and closing a gate. I'm intentionally using these words so that what follows you're able to corroborate. So 0 to 1 and 1 to 0 is nothing but digital technology. So if semiconductors are made to conduct and insulate and block and open, etc., they can very easily handle digital technology. Now, this particular aspect is achieved through controls of the gate, which I was talking about. You can have this control of the gate through a junction. I'm using very simple words, just remember this. Through a junction of two compatible semiconductors. This junction has to be made. In the industry, you have to make this junction, right? And the gate length is measured in nanometers. So this gate which you're talking about is normally measured in nanometers, and 1 million nanometer make a millimeter. So you can imagine how short, how small is the gate. But this gate has to be controlled by some method so that it can open or close. Now, it is very difficult to make gates of very small nanometer values because they are so small. You have to see it under a microscope to make sure that what you have made is working properly. But smaller the gate, it is more efficient because it takes less time for it to pass through the gate, and therefore it is fast acting. It takes less power, dissipation of heat, etc. The advantage. So I go back to my original presentation. As far as semiconductor is concerned, I finished. Main thrust in semiconductor industry is to make gates by some method, and the gates are normally in nanometers. That much you should remember. Let me go back to the presentation. Main. Okay. Now, semiconductors have become very versatile, advanced, and extremely compact. And I've told you, it's all used in all your domestic appliances, even for healthcare equipment in the hospitals and machinery in industry, cars, entertainment, etc. Now, there are two materials which are used to make semiconductors. Just two. There are many more, but the major is two: silicon and germanium. You can see in the first part of the slide, silicon is actually available in the earth as a form of sand, silicon dioxide. You heat up the silicon dioxide along with carbon. Carbon will take away the oxide and only silicon will remain. And from that molten silica, you make silicon crystals. In the world, 8.8 billion tons are made in a year. And just remember, China makes 6 million tons out of this 8.8. So the industry required for making just the silicon, pure form of silicon, is mostly in China. You heat up sand and you get silicon. Of course, you consume a lot of power. And thereafter, you get silicon crystals. Similarly, for germanium, ore is refined to germanium crystals. And look at that. 140 tons are made in a global, and China makes 95 tons. Germanium is not so popular as silicon. Primary semiconductor material is silicon. Now, when you make silicon crystal, you heat it up and hang it in the center of a cylindrical container and rotate the container. The crystal will become bigger and bigger and bigger as it becomes attracts more electrons from that molten one, and you will get a shape something like this, which I have shown. It's called a bowl. This shape is called a bowl. So what you do is molten crystals are spun, as I told you, to form circular bowls of different diameter. Some are thin, some are thick, but they are made through a centrifugal process. Thereafter, bowls are laser cut to form circular cross sections called wafers. So you see some 4 types of bowls in the photograph below, and you can cut them to small thin wafers, which look very, very thin, of course, in this photo. It's correct. But I was trying to say it is something like your pizza base. You make this, that becomes the base. But here it is very thin, called a wafer. And the diameter of wafers are indicated in millimeters. So we have come to 2 dimensions now. Gate is normally in nanometer, but wafers are in millimeter. Right. Thereafter, you look at this display of different wafers from 450 mm to 100 mm. 450 mm is the biggest wafer made in the world today. Some industry in Korea has made this 450 mm thin wafer. And This wafer's diameter is, as I've shown you, varies up to 450. But thickness of wafer is in micrometer. So I need to once again repeat. Junction is in nanometer, wafer diameter is in millimeter, and thickness is in micrometer. 1000 micrometers make 1 millimeter. So you can imagine how thin this wafer is. Very, very thin. And you can compare this thickness of wafer. It is normally between 275 to 925. And we will not look at handling this by hands because they're very thin. But for comparison, human hair is 50 micrometers, human hair. So some of these wafers are as thick as only 9 human hairs put together, and some are less. Now, the bare wafer is bought by a chip manufacturer or a chip designer. So wafers are made by a different company. There's a separate factory for it. They make wafers of silicon of different diameter, different thickness, and make it available for the next process. So let's go to the next process. Wafers, once they are made, they go through a very complicated process of making electronic components on the wafers. I will not go through this complete process because they're quite complex. There are many people who are not engineers in this audience. So I would say you create a pattern on the wafer. Let us say you want the wafer you are selected. Let us say you selected a wafer of 200 millimeter dia. You want to make 10,000 transistors you want to make on that wafer. So you create a pattern. Let's say 1,000 in one group, another 1,000, another 1,000, another like that. 10,000 transistors you made into that. You make a pattern, and based on that pattern, you make some deposition, some photoresistant coating, photolithography. That means with great accuracy, you do some pattern on the wafer, and then you etch it. All these are done by machines under electron microscope. So you make this design on the wafer. So please remember, first to make a wafer. The second step is you make a pattern on the wafer. It's in another factory. It's in another line of the production line. Then once you have made this deposition and everything ready, you cut the wafer into small bits. I told you, whole wafer at 10,000 transistors, you make clusters of 1,000. So you cut a small portion, which has got the 1,000. Similarly, you cut every cluster of 1,000. I'll show you a photo, the next slide. So these are called dies. So we come to another technical term. First was wafers, then it is dies. And dies are small, 3 mm by 3 mm square, in which 1,000 transistors are there. And they become the building block for the designer. A designer who makes a circuit, he wants transistors. So he takes a die which has got 1,000 transistors. I'm just giving a number, 1,000. It can be even larger, it can be smaller also. So he takes that and then he makes a design of an electronic circuit with this 1,000 transistors in the die. So 5 things we have discussed till now. Nanometer is for junction. We have still not come to the junction. Thickness is in micrometer. Diameter is in millimeter. And then wafers are converted to dies. Can you see this photograph? This is a wafer which has been cut into dies. And you can remove the dies and thereafter use the dies for your electronic circuit to be made. Let us see how that is made. So you integrate all these dies. You selected one die of 1,000 transistors. You select another die of some other function. You take a third die, let's say, which is for an oscillator, fourth die for something else. So you put all the dies which is in your design together. A chip designer selects dies which are required for his product, and then they are laid and bonded on an epoxy layer. He puts all the dies on this epoxy layer, which I told you is a very small area. And the interconnections are made between the dies. Die to die, there are some connections. They have to be, one is input, one output has to go to input of another. So all those connections are made through wires or tracks which are laid, all done very, very minutely under electron microscope. And one completion of all this, the dies which have been laid on epoxy is packed as a chip. And the chip is given external connections with pins for putting it in the PCB. So integrated chips have got dies in them, and dies are actually cut from a wafer, right, after doing the pattern superimposed on it. Sometimes ICs have more than one wafer. Till now, we're talking about one wafer cutting into dies, but ICs can have multiple layers of wafers and multiple layers of ICs vertically also connected by some method of boring, drilling holes in them, and through which connection is made, so that the integrated circuit is compact, it can do all the function. This is how integrated circuit looks. You can see these are external connections. This is about maybe about 2.5 centimeters by 2.5 centimeters. You see a big one and you see a small one here. These are all examples of ICs that have been finally made. So let us look at the ICs and chips. The integrated circuit is called a chip, which I got, as I told you, wafers and dies. And they are custom made for your application. Sometimes they are made only for digital application. They're called digital ICs. Some are made for controlling some electromechanical items. Then they have analog ICs. So you have different functions, custom made ICs accordingly available. And then the pin connections are made to the PCB. Now you see another photo. This is another IC with large number of external pins, but internally it must be having something like 10,000 or 15,000 transistors, which will do all the function as per design. So where are these ICs used? ICs are used in digital ICs, as I told you, for computers, programmable ICs, etc. Mostly where digital data is used. Analog ICs are used when you want to have filters, oscillators, flow sensors, pressure sensors, pacemakers. Pacemakers have got analog ICs because they have to stimulate the heart in case there's a requirement. Catheters, which are used in medical devices for measuring flow of liquids, maybe of blood or maybe of sometimes a urine, etc. Then they have analog ICs used. Cameras also use analog ICs because you have to have control based on light. You want more light, less light, background. So all those controls are made using analog ICs, which are specifically made for the camera. And there are which are using power chips, which are actually used for switching on your inverter. I'm just giving an example. Your inverter switched on suddenly when the power goes off, or it is switched off when the power comes back, or in some other circuit where you have, there are many electronic engineers perhaps in the audience, where IGBTs and thyristors and all are used, you require higher current to be handled. Obviously, the junction required in this will be bigger than what is required in digital. So power chips are classified separately. So ICs or chips are in 3 groups: digital, analog, and power. And there are semiconductors available for different functions. I'll just give a run through it. There's silicon carbide used for radio detection. You want to have a debit card which has got a chip, but you want it to operate through Wi-Fi with the cash counter. Some radio detection is required. You go for silicon carbide chips. Gallium nitride is used for power devices, lasers, photonics, like they use in solar panel, and green LEDs. You want green LEDs in your house, lighting? that will be gallium nitride. Gallium arsenide is used for high-speed communications, like 5G is coming in. Gallium arsenide ICs are used. Lead sulfide is used for infrared sensing. If you want to have infrared sensors to be fitted in where machineries are there to measure temperature, or these days infrared thermometers are available to look at the temperatures of patients. Use a chip inside that, which is made of lead sulfide. And gallium phosphide is used for red LEDs, and copper iodide is used for blue LEDs. So I have talked about different material which are used for different functions, but the major thing which is used is silicon. And then comes germanium. Then all this for different functions. Now I come to almost end of this part of this presentation. Before I go there, I want to talk about one of the latest developments of chips which have come in the world. It is called bionic eye. In Australian university has made sometime in December 22, it has finished with all the trials, where a person who doesn't have vision, he has been provided with a bionic eye. He can see without an eye now, because inside the bionic eye, which looks like an eye, but is actually not, it has got a camera, which takes all the photographs of what the camera is seeing. And that camera output, camera is again made out of a chip, and that is converted to a format which the optical nerve, you and me have got optical nerve which is feeding our brain, but this man's optical nerve may be not working efficiently, or the optical nerve has got disconnected from the eye, retina. So they make a connection to the optical fiber to the brain, and he gets complete vision using a bionic eye. This is one of the latest developments which semiconductors are brought. I thought I should share it with you, but let's see some of the other recent applications. First, it has gone in a big way for computation and data storage. You can appreciate that. Industry 4.0 applications and artificial intelligence, they all use a lot of chips for operating and giving decisions based on the inputs which are coming for the chip. Communication 5G, I talked about a particular type of semiconductor used in that. For spacecrafts and transportation, when I say transportation, I include cars, ships, aircrafts. They all use a lot of ICs in their electronics. And spacecraft and aircrafts which have to fly, they're looking for saving weight. They want the electronics to be compact. Obviously, ICs will be preferred. E-passports. I just want to make a mention. India is going to get e-passports in 23-24. About 1,000 crores have been given for this in the budget 2 months back. What this means is the passport will have a chip which will be read at the immigration counter. And that protocol is universal for all the countries which have opted for e-passports. Of course, it's very similar to a debit card being read. It's very similar to your credit card being read. But once it is read, the contents of e-passport, which is codified, you can't make out anything out of that data. It goes to another server where it is juggled around and converted to one layer. Then it goes to another server where it is juggled around and converted to a third layer. So it goes through a lot of data decryption, and it is decoded. And finally, your photograph and your fingerprints if required, or your biometrics of the eye, all these are required, is available to the immigration counter. It is understood that e-passports become difficult for people to sort of create a fraud. So India is going to get e-passports very soon, but India is pretty late in this. 100 other countries already gone for e-passports. So, but we are making progress on this front as well. Drones, again, use a lot of chips. Healthcare, medical device, I talked about a pacemaker and catheters. There are so many CAT scan and so many other electronic equipment used for imaging And that is in a big way using semiconductor devices. Now, the last point which I want to talk on this part is, Koreans have recently said they made a 3 nanometer gate. Remember, gate length is measured in nanometers, and they said they have made a 3 nanometer of a gate. That is 1/1,000,000th of a mm is 1 nanometer. So there have been a lot of discussion on this, and finally, scientists have confirmed it is not possible to make a 3 nanometer gate physically. No machine, no laser, no microscope can enable this sharp precision 3 nanometer gate. So if you hear somebody saying 3 nanometer gate or 5 nanometer gate or 8 nanometer gate, please remember, they don't represent the correct length of the gate. They represent a technology used to make sure they are more efficient by speed of response. But physically, they are not 3 nanometer. What exactly they are equal to physically, that is not being openly available in the internet, in the public media. But suffice to say, such less than 10 single-digit nanometer gates are a question mark. They represent technologies by which, I'll just give you an example, a 20-meter gate, 20 nanometer gate can be made to work faster by some other technology, and they are as good as a physical 3 nanometer gate if achieved. That means the 20 nanometer gate is made to work faster by some method, and they're as good as a 3 nanometer gate if achieved, but which is not achieved. So just want to share this little bit of smoke and mirror issue on this nanometer gate. So don't believe if anybody says they have got less than 10 nanometer gate. It is not physical length, it is technology which is representative. So with this, I want to conclude. There are 4 stages of manufacture of a chip. First is wafer. We discussed that, wafer cutting. Second is die cutting after you have put the pattern on it. That's in another factory. Third, somebody does the design. He selects one die of this size, another die of this size, makes a circuit, he designs all this, and he tells the 4th person, you put all these dies together on epoxy, package them, give external connections, and IC is ready. These are 4 stages. And in India, it's only the 3rd stage which is available. Our R&D labs, our private industries in Pune, Bangalore, and in Noida, they are doing a lot of work on design of ICs. That means they know a company wants this type of IC to do this function, maybe for a washing machine or maybe for a car. Then he will design a circuit and select dies which are available in international market. And then he'll make a circuit and give it back to the customer saying, this will work, you take it. And that IC is made and then tested. So India's participation IC manufacture today is in design only. There is no physical work of semiconductor, wafer cutting or die cutting or packaging is not there. So at the end of session 1, we have understood the technological complexity of IC manufacture and how India is presently doing design of ICs, which is more of software work, which is more of laboratory work than in industrial work in factories. Okay, so let us go to the next. Why does India want to manufacture this? Why does India want to manufacture? Be happy in importing it. So some reasons I will tell you. In India, which is $3.5 trillion GDP now, almost $3.5 billion, 26% is industry and 56% is services. So in industry, electronic equipment, I told you some time back, Bharat Electronics makes electronic equipment, ECIL makes, Mahindra makes, Tata's make, all industries put together, electronic equipment is 2.25% of GDP. There is no contribution from semiconductor manufacture in industry sector. Design comes in services sector, not in industry. Okay, so no manufacture in India of ICs. And all this equipment which has been made in India is using ICs imported. So their net contribution to GDP is 2.25 minus the import cost of all ICs. So it'll be less. In services sector, only 0.7% is contributed by design efforts of ICs and dies, which Indian companies are making. So very small amount, but they are doing good work. They are doing quality work and is likely to attract a lot of commercial offers from various countries. So domestic manufacturing is based on imported IC, which I told you earlier. Now, imports of semiconductors. India imports semiconductors. Semiconductor imports have grown from 46 billion to, I can't see this. I can't see it on my screen. To some higher value in 2021. And the major imports,
54 billion.
54 billion, sorry, because some other label is coming on top of it. So in 2021, we have $54 billion ICs and some other semiconductor components imported in India from China, Taiwan, Korea, Japan, Vietnam. I've only said 5, there are some more, but these are the major ones. This is expected to increase to 80 billion by 26. India's crude oil is 97 billion in 21. So you see how close semiconductor import is coming to crude oil. As such, India doesn't have much of oil from domestic resources, only 15%. 85% of oil comes from abroad, and that is only 97 billion. And that is going to go down because there's a renewable energy is growing for higher. So at some stage, semiconductors will overtake crude oil. So if you say semiconductor is a new oil, it is correct. Our highest imports will be on semiconductors very soon, another 5 years' time. Okay, by 2030 you keep. We will be importing more semiconductors than petroleum or crude. It's a very significant factor for us to understand, for our economists have addressed this issue, and they have identified 7 compulsions why India has to manufacture chips. India has no option. Semiconductors are going to be the heart of economic growth in future, with everything becoming electronic, everything becoming digital, everything becoming artificial intelligence based. We have to have semiconductor base in the country. Otherwise, we'll be dependent on imports, which I told you, which is going to be more than crude oil. Then India has rich reserves of rare earth element, which is required for making semiconductors. Almost 6% of global supplies with us, but we are not doing the mining at all. So enough earth resources are available with us, natural resources are available with us. So we don't have to worry about resources to make. We have to only set up factories, infrastructure, and facilities to, as I told you earlier, make refined silica, make wafer, cut dies after pattern imposition, and the design you already have, then do packaging. So this will obviate our present risk in supply chain. You have seen the countries from whom we are importing. More about it in the next slide. So if you keep on importing, if you keep on basing our economy only on imported ICs, you will find it difficult. Like we felt it difficult during COVID. Chips didn't come from abroad. So cars cannot be given second key. Car sales also dropped, which picked up later. Defense and aerospace equipment requires a lot of semiconductors. So there's a risk in supply chain which has to be overcome. And you also understand there's extensive digitalization of economy, 4.0, 5G is almost there. So if you do semiconductor manufacture in India, it also helps us our overall mandate of Make in India and Atmanirbharta. It will build matching industrial capability to the design competence we have. We already got design competence, but we don't have industry capability. So we build a matching capability. So we make overall progress in IC manufacture, which we can use for our equipment. And if there is still something available over and above that, we can export it. So what is India's mission for manufacturing some semiconductors? I finished on the second part. I think I hope I have convinced you that why India has to make manufacturers very soon, manufacture semiconductors very soon. So
Yes,
what is
yes.
India's mission to do this? We had from sand, you have to come to chips. You have to make this. So semiconductor manufacture, we initially ignored this field because we didn't do mining. We didn't set up industrial infrastructure. Then government had to set up some R&D facilities in Chandigarh, some in Pune, some in Bangalore in the initial 3 decades, but they were having limited success. Most of these, all these were in public sector. But in the last 15 years, many private design labs have sprung up, as I told you earlier, in Bangalore, Pune, Noida, etc., who have consolidated India's status as chip designers. I told you earlier, we got capability for chip designing. After due deliberations with all stakeholders, government decided to launch a mission in December 22, and we are talking in April 23. So 4 months back, decided to launch a national mission to make semiconductors in the country. So I'll speak more about it, but on the left side of photographs, just remind you, we got sand, we had to make silicon, we had to make wafer, and we had to make chips. These stages we had to cross. So India's semiconductor mission was created in December 22, as I told earlier, as an independent business division of a digital corporation company, which is a no-profit organization under Ministry of Electronics and IT. So this was launched as an independent business division, December 22. I'll use a short form ISM. It has got administrative and financial powers to enable and to catalyze India's semiconductor ecosystem in manufacture, packaging, design, etc. And government has given 76,000 crores for undertaking this activity, and they will give support. Those who come forward saying, I will make semiconductors in the country, and government will support them. More details about it in the next slide. But they said advisory council with international experts, that who is coming forward? Is he a bona fide one? Is he capable of doing it? Does he have international collaboration? Because nobody has got capability in the country. If you want to make anything in the country, you have to have an external collaboration with a foreigner or foreign company. It could be a government. So there's an advisory council which looks at all this and clears the various cases, proposals which have come forward to make chips like this. Can you see the chip size of it? And the small dots which are there are representing a chip. These are actually the connections, but above them in the upper layer is the chip. So ISM's offer to industries is 50% project cost. They will support a company who wants to make a chip below 28 nanometer. If you want to make a chip less than 28 nanometer, I told you the junction length, gate width. If it's less than 28, government will give you 50%. 40% if it is from 28 to 45 nanometer, because that is not so complicated, so complex. Equipment required are not so expensive. The microscope, the laser cutting, various things are not so expensive for 28 to 45, and 30% for 45 to 65. 50% they will give you if you want to make LED and LCD displays. Could be for TV, could be for computers, etc. Please remember, not a single LED, not a single LCD display is made in the country. not even one. All of them are imported. Label may be changed, but the production is abroad, not in the country. So if you want to set up an LED, LCD display company, government will give you 50% support. And if you want to start something for silicon photonics, which are required for solar panel, they'll give you 30%. And if you want to set up a new design lab, like some have already started, 50% government. So this 76,000 crores, which was allotted, will be given to proposals coming from different people based on these guidelines. Now, I want to see the global trend. I want to share with you. Spend a time on this graph. Look at 1990. The people who were making were blue, yellow, and red. US, Europe, and Japan. Almost 100% was being made in 1990s by US, Europe, and Japan. Then slowly South Korea came, Taiwan came, China came, and you look at the other colors. China is here. This is Taiwan. This is Korea. They are manufacturing more than 50% now, while they were doing 0% in 1990s. And US, Europe, and Japan have reduced in their market share. Maybe they're not increased because the demand has also increased. So what they were making 100% earlier has come down to 35% now by quantity because demand is more. But the fact is they are not the dominant players in the market today. US, Europe, and Japan are not. It is Korea, Taiwan, and China. There are others also, Vietnam and somebody else, Indonesia, Philippines or something like that, but they're having a very small percentage. So the global trend in manufacturers, it has moved away from West to Asia. And the new leaders, as I told you, are China, Taiwan, and Japan. And all of them have set up this with huge support from their respective governments, just like India is trying to do now. They had huge support, incentives from the government. So US is finding that growing dominance of China in semiconductor, and Taiwan is anyway in a difficult state with respect to China. So US is looking at how to counter this China's dominance. So they formed a Chip 4 Alliance just 7-8 months back in August 22. US, Korea, Japan, and Taiwan have joined together to form a Chip 4 Alliance and to reduce Chinese dominance. Now, many companies in China are funded by foreign countries like US. Their companies have set up a factory in China to make ICs. Now, US has come out with some orders, which will come in subsequent slide. Sensitive chips will not be made in that factory in China. It will be made elsewhere. And what China may make, maybe for washing machine and refrigerator and some other domestic appliances or cars or something. But the sensitive ones which are required for spacecraft and defense equipment may not go to the factory located within China, even though it is owned by US, right? Now, in India's case, the ISM package is expected to enable Indian industry, new people coming forward, to get production facilities from abroad, set it up a factory in India, and create a matching facility to the existing design expertise. An MOU was signed with last month, March 23, between India and US. It was signed where India aims to make sure innovation and supply chain risks are reduced, and we are able to boost our domestic technical skills. They are also looking at the manufacturing ecosystem, how it can be built up in India very carefully. It has been nourished because manufacturing ecosystem of semiconductors requires stringent quality measures. I've very briefly told you about the complexity, and it's a long haul process. A lot of testing is required. A lot of debugging will be required as soon as they're set up. So India wants to make sure this ecosystem is set up in a very calibrated and quality conscious manner. There are 4 companies which have come forward: Tata, HCL. HCL is a design company. Tata is also a design company. Vedanta is a company which has come afresh with Foxconn. You must have read in the paper saying that they will set up a factory in Gujarat. Then there is a Dutch company, NXP, which it has got an office. It has got a supply lines as well as the design office in India. They are planning to expand it to manufacture. So these cases are at the moment with the government after they issued the ISM document in December 22. And India is focusing only on chips above 50 nanometer. And this is what I want to emphasize on. India is want to cut the teeth only on 50 nanometer and above. One, it is first you have to make in chips of gate length little more to establish ecosystem. Second, India's immediate requirement is chips required in renewable energy projects, power projects, power chips. So power chips, India wants to look at 50 nanometer and above so that our industrial requirement for energy sector is taken care of to start with. Thereafter, you can look at the lower chip length. And USA, as I told you, has signed a pact in March 23 to establish supply chain and innovation ecosystems. So in 2030, how will ISM look like? India's mission, how it will look like? Let's just extrapolate the present activities and see how it is. India's electronic equipment manufacture will be, it is expected to be 24 lakh crores. 24 lakh crores of electronic equipment will be made in the country. But 8 lakh crores, almost 1/3, not almost, exactly 1/3, will be imported ICs. Because by 2030, you may not be able to set up an IC manufacturing company in India. Or you may just about you must have made. And so it is expected that we'll be importing, mostly imported, we'll be using in electronic equipment manufacture. Finally, the ICs that we made for equipment only. Second, global IC manufacture is expected to be 1 trillion in 2030. 1 trillion, that is 1,000 billion. But India is expected to make only 5 billion. 5 out of 1,000 billion. So India would have made a very small and a slow start by 2030. Expected mostly from new firms which are going to locate in Karnataka, Tamil Nadu, Gujarat, etc. And manufacturing chips which are 90, 65, and 45. So these are the chips which are going to be likely to be made, more on 90 and 65 and less on 45. The ongoing chip war between USA and China is likely to become more aggressive as the years go by towards 2030. Because Chip 4 Alliance is going to restrict the type of chips which China-based factories can make. And second, USA has passed a new law called Chip and Science Act in 2022, just last year. Based on that law, a lot of restrictions are placed on US firms in exporting chips to companies which are based in China, or exporting to countries which are producing Chinese equipment. So the geopolitical situation is going to become different, and India is making a small start by 2030. 5 out of 1,000, I told you. And but India's labor rate is very competitive. Our design capability is well established, and government's incentive scheme is expected to make the chip making dream a boost. So after 2030, it is expected to pick up pace and we'll be manufacturing more chips. So till 2030, it's a small beginning. While design is going on, manufacture will be a small beginning. So finally, chip making is a long haul process, which requires two major resources, water and power. Water is required to make sure the refinement of silicon and cooling of various equipment, lasers and other things are done with very high quality, high grade purity water. And power is required in large quantity. Uninterrupted power is required. So this is a challenge for India's power sector. It's a challenge for India's water sector. So we have to look at these resources as well. And we haven't started mining yet of silicon dioxide. So you may be wanting to establish factories to make chips in India, which many people have come forward, but you need to have raw material mined in India and made available, the pure form. You need to make sure high-grade water is made available to these factories. You need to have uninterrupted power made available to these factories so that they can make a beginning in semiconductor manufacturing. That is why by 2030, we would be establishing a manufacturing facility for chips, and the total value will be only $5 billion, as I told you earlier. And that also for high nanometer IC chips, which is what we want for our power sector. So with this, I come to my last slide on conclusion. Semiconductors are now an inseparable part of our life. And they're going to soon become, the part is going to become heart of our economy. This is the prediction of economists. Semiconductors will overtake oil. It's a new oil which is going to be in power play. India has at the moment no facilities, manufacture, but design-wise we are fairly well established. Our imports, if allowed to grow the present manner, it will overtake oil very soon. We have to reverse this condition by starting manufacture in India. The semiconductor mission is the first step which the government has taken with good incentives, as I mentioned to you earlier, and a lot of foreign collaboration. Recently, the pact with the USA will help in supply chain. So you may not be able to mine and make silica immediately in India. US will be able to help us with the supply chain of some of the items and including some machines and equipment which are required for manufacturing. By 2030, I already told you we are expecting only 5 billion in high value, high nanometer chips. And chip making, once it starts, along with chip design, which you already started, will make India a prominent player by 2040. By 2040, you may be able to supply 10% of global supply. By then, 2030, very small contribution, but in 10 years, we expect to come up to 10% player in semiconductor industry. With this, ladies and gentlemen, I conclude my presentation. Jai Hind, thank you very much for your patient hearing.
Thank you very much, sir.
Yeah, about Admiral Kannan,
Yeah,
you will allow some time for discussions?
sure. I'm stopping my sharing. I'm open for discussion.
Okay. So one of the thing I want to say, TSMC, Taiwan Semiconductor Manufacturing Company. So what I understand, they are making about 60% of the world demand of semiconductors. And they claim that
Can you repeat the name of the company?
TSMC, Taiwan Semiconductor Manufacturing Company.
TSMC,
And,
the very famous company. Yeah.
yeah. So what I read, is they are covering the 60% of the world markets. And lately they are building a factory in USA, somewhere in Texas or so. That factory cost is $14 billion. That is the cost of the project. That also making 3 nanometer semiconductor chips. And another thing, with due respect, let me correct that 1 nanometer is 1 by billion, the 10 raised to minus 9 meter.
That's what I said. 1 millionth of a millimeter, Matthew.
Yeah.
I said 1 millionth of a millimeter.
One millionth of a millimeter.
Yeah, and
So,
1 billionth of a meter.
Yeah, so that is 1 billionth of a meter. So you are right and I am wrong. So I got
We are saying the same thing only.
Okay, never mind. I corrected that. It is 1 millionth of a millimeter. Then it is okay. It is okay. And another thing is, in India, we used to say a terminology that lakh cross. That is 10 raised to 12. That is 1 trillion.
I will decode it for you if you want.
Yeah.
1 lakh crore. Just remember, all of you. Very simple.
Yeah.
1 lakh crore is 1 trillion.
Yeah, 1 trillion. That is
Okay,
12
very
zeros.
simple.
Yeah.
So, but you should say what currency. If you say rupees 100 lakh crore is rupees 100 trillion. I'll give another example. 80 lakh crore is 80 trillion.
Yeah.
So
lakh
80
crores,
trillion,
but India,
80 trillion rupees is $1 trillion.
Yeah, in India, we are more usually using the terminology lakh and cross. That is why it is coming. Otherwise, in the international arena, we are mostly used to the trillion instead of lakh cross. And another thing, and I am openly saying, one of my business is manufacturing of semiconductor chips. If anybody can help me in this, welcome in the open forum.
Okay.
So, I'm not kidding. I'm not kidding. I'm not kidding. I'm serious.
Yeah. So can I respond?
So what I said, I am not kidding. I am very seriously saying.
Agreed.
I will give my LinkedIn site, the link of my LinkedIn site. Then if you take a look that, you will understand I am not kidding.
Okay. So 2 points I want to once again reiterate.
Yeah.
There are many engineers in this group.
Yeah.
So what I said was, if you want to make a chip, there are 4 stages.
Yeah.
You have to first mine.
Yeah.
And then make wafers.
Yeah, that is right.
Second is
for solar power also. This is there. Same process for the solar power.
Same process. No. If you want to make a chip, which I told you, silicon photonics. That is for solar panel.
Yeah.
So first thing is you have to make a wafer.
Yeah.
Second,
you have to melt that silicon.
Yeah, you have to melt silicon, make crystal, make a bowl, cut it with laser, and make wafer.
Yeah.
Second, you have to make a pattern superimpose on the wafer by very complicated chemical and photo lithography techniques.
Okay. May I interrupt you 1 minute? So
Yeah.
there is one factory, probably 1 factory or 2 factory in the whole wide world, which is making the dies and equipments for the manufacturing process of the semiconductor.
Yeah, I'm coming to that.
That is in Netherlands or somewhere.
I'm coming to that. There is, so to make this deposition of the pattern, then make sure photolithography techniques are applied, etc. The equipments required are extremely expensive, and there's only one company, as you said, I think it is ASMC company, ASMA.
Yeah. Yes.
In Europe, they're the only people.
That is in Netherlands.
90% of the equipment is supplied by them.
Right? That is only one company. That is why I told it is monopoly. ASMC or something.
Correct. And Taiwan, as you said, the Taiwan company is presently supplying huge quantity. But I want to reiterate one last point when you said 3 nanometer. Please believe 3 nanometer gate is not physically 3 nanometer. It is functioning as if a traditional technology 20 nanometer, if it is shrunk to 3 nanometer, how it will perform, that they have been able to do by improving the technology on a traditional 20 nanometer gate. So exact what is internal technology that which they have made is not available in the public media. So 3 nanometer gate, if they say, is a technologically enabled gate, but physically not 3 nanometer. Just remember that.
Okay. I noted this point. I noted down this point. 3 nanometer is not correct, even though
No, 3 nanometer is not physical length. It is a technologically enabled gate. Okay, I've answered all your points.
And this is Samsung Electronics in South Korea. They are making, they claim it is 5 nanometer. I don't know. The Samsung Electronics, they're very strong in this.
My understanding is anything less than 10 is difficult to be achieved by laser cutting. And therefore, they have tried some other technological methods by which they can fasten the electron movement within the semiconductor, and thereby time is reduced to cross the gate. So it is as good as a narrow gate, but actually the chap is running faster there by some technique. I don't know how it is being done. Okay. If anybody, any other questions over there?
Okay, എന്തെങ്കിലും ചോദ്യങ്ങളുണ്ടെങ്കിൽ ചോദിക്കാം. എന്താണ് പുതിയ ലേറ്റസ്റ്റ് ആയിട്ടുള്ള സെമികണ്ടക്ടർ ടെക്നോളജിയുടെ പൊസിഷൻ എന്ന് സാർ വളരെ കൃത്യമായിട്ട് എക്സ്പ്ലെയിൻ ചെയ്തു. പറഞ്ഞതുപോലെ ഒരു ന്യൂ ഓയിൽ എന്ന് പറയുന്ന ഒരു കോൺസെപ്റ്റിലേക്ക് മാറുമെന്ന് പറഞ്ഞു. അതുപോലെ പുതിയതായിട്ട് ചിപ്പ് മാനുഫാക്ചറിന് വേണ്ടിയുള്ള അസോസിയേഷൻസിനെ കുറിച്ച് പറഞ്ഞു. ചിപ്പ് മേക്കിംഗ് എന്ന് പറയുന്നത് ഒരു ഹ്യൂജ് ഡിമാൻഡുള്ള ഏരിയ ആണെന്നും സാർ പറഞ്ഞു. വേറെ എന്തെങ്കിലും സംശയങ്ങൾ ആർക്കെങ്കിലും എന്തെങ്കിലും? ശ്രീകുമാർ സാർ, can you hear?
No, this is a very gray area for me. This subject.
So Admiral Kannan,
Yes.
I heard an observation to manufacture the project cost of a refinery. We have a 4th refinery in Kuwait lately. Its cost is about 14 billion US dollar, 14 billion. And that is a very big refinery. I don't know what is the production capacity. And this TSMC's new factory in USA, which they started lately, or they started the project, that also cost 14 billion. So in a nutshell, you can say the investment required for manufacturing a semiconductor is of the size of building a refinery. It is such very, very expensive.
Yeah, very expensive.
Very expensive.
That is why government is giving so much of incentive, because no industry can put so much of money, capital money, to start a industry. And not only it's capital intensive, it is also time taking to establish.
Yeah.
Sabu, anybody else?
Anybody else? വേറെ ആർക്കെങ്കിലും എന്തെങ്കിലും ഡൗട്ട്? സർ, can you help? ശ്രീകുമാർ സാർ പറഞ്ഞില്ലല്ലേ? പറയൂ സാർ, പറയും.
നമുക്ക് ഈ പ്ലാറ്റ്ഫോമില് ഒരു ക്ലാസ് കിട്ടിയത് തന്നെ വളരെ ഭാഗ്യമായിട്ടാണ് ഞാൻ കരുതുന്നത്. SLMA, what is chip, what is semiconductor, how is created, and moreover, what is the importance to create this section in India. ഇന്ത്യയെ സംബന്ധിച്ചിടത്തോളം ഇത്രയും ശക്തമായ ഒരു ആയുധം ഒരു വളർച്ചയുടെ പാതയിലേക്ക് എത്താൻ സാധിച്ചുകൊണ്ടിരിക്കുന്നു. ഇൻവെസ്റ്റ്മെന്റ് കൂട്ടിക്കൊണ്ടിരിക്കുന്നു. അമേരിക്കയുമായി നല്ലൊരു ഒപ്പുവെക്കൽ MOU ചെയ്തിരിക്കുന്നു. ഇങ്ങനെയുള്ള അറിവുകൾ സത്യത്തിൽ ഒരു ലേമാൻ ഇല്ല. അത് കണ്ണൻ സാർ വളരെ കൃത്യമായി നമുക്ക് തന്നു. ഒരു നല്ല ഡിസ്കഷനും അതിനിടയ്ക്ക് നടന്നു. താങ്ക് യു സർ. താങ്ക് യു വെരി മച്ച്. താങ്ക് യു.
And I wish to congratulate Kannan sir to convince the participants. And I have one from Switzerland, the electronic passport. I'm an electronics and telecommunications engineer. So I know I have studied this.
Where you are speaking from now?
I'm from Switzerland.
Switzerland.
Switzerland. What
Switzerland.
is your name? What is your
Thomas.
name, please?
Thomas.
Tom,
And Matthew Varghese.
can you just increase your volume a bit? Come closer to the mic.
Yeah, Thomas,
Yeah.
my name is Matthew Varghese. I am speaking from Kuwait.
Okay.
Tom പറഞ്ഞോളൂ. Tom.
സാറ് ഒരു ലാൻഡ്മാനെ എങ്ങനെ അവതരിപ്പിക്കാം, എങ്ങനെ പ്രസന്റ് ചെയ്യാം, കൺവിൻസ് ചെയ്യാമെന്ന് വളരെ സിസ്റ്റമാറ്റിക് ആയിട്ട് അവതരിപ്പിച്ചു. അതിൽ സാർ വിജയിച്ചിട്ടുണ്ട്.
Thank you.
Thank you.
Thank you, Tom.
Srimar sir, unmute you. Srimar sir, unmute you. Unmute ചെയ്തു. ഞാനൊന്ന് മ്യൂട്ട് ചെയ്ത്.
ശ്രീകുമാർ അൺമ്യൂട്ട് ചെയ്തിട്ടില്ല.
ചെയ്യാൻ പറ്റുന്നില്ലേ? Yes. Now you can
Now
speak.
it's okay? Yeah,
Yes,
yeah.
yes.
It was a very wonderful speech that only people like us can now understand what actually chip is and how these microchips are all made. The semiconductor subject is also a very vast subject for people like us. So he very elaborately he told everything in details. So I am very much understanding all this about how they are made and how much India is struggling to get into this market. And really, it is worth thinking how it is overtaking the fuel in cost wise in future. It's a gigantic pressure. So thank you, Kannan, for your wonderful.
Thank you, Sri. Thanks for the opportunity to. Thanks for attending. Thanks to Sabu also for giving us opportunity.
So thank you very much, sir. Once again, we are waiting for the next session. Very wonderful session.
Next session, May മാസം കാണും.
Sure. We are waiting for. Thank you.
Looking forward for another speech.
ഒരു സെഷൻ മഴയ്ക്ക് മുമ്പ്
Every month you are presenting, Kannan?
Yes.
Every month I am trying to present topic ആണ് പ്രശ്നം.
Yeah. No, to prepare also it is pretty hard. No, I am planning to do some presentation to Kuwait Society of Engineers. I had been thinking for a long time, but it requires a lot of preparation. It's pretty hard.
See,
yeah.
I've been telling Sabu it takes me nearly 3 weeks to prepare. So 1 week before Sabu gives me a date, my PowerPoint presentation is almost ready.
Kannan, you are really resourceful person.
Matthew sir, present ചെയ്യും. അപ്പോൾ കുവൈറ്റിലേക്ക് വളരെ ഈസി ആയിട്ട് present ചെയ്യാൻ പറ്റും.
Yeah, probably if I am presenting, I do one thing, I will make a link to our 73 batch also. So I don't know when I am going.
You are welcome. You are welcome.
Yes. Anybody is interested, definitely we can have some presentation also. Anyway, I am doing every day. Every day I am doing. So it's a better way.
So what is your number? What is your number, Sabu?
സാബുവിന്റെ ബാക്കിൽ എഴുതിയിട്ടുണ്ട്.
9447 92271.
Let me write 999. Can you repeat?
4471.
I didn't get. I got 944.
Matthew, you can
look at Sabu's photo. Sabu's photo ബാക്കിൽ എഴുതിയിട്ടുണ്ട് നമ്പർ.
പുള്ളി സീറ്റായിട്ടുള്ളതാണോ?
കാണുന്നില്ല സാർ, നോക്കിയേ.
ഇല്ല. You can watch in the link with this photo that there is the number is written.
Okay, let me. Anyway, you said the number 944
71 922
922
71.
Again 71.
Yeah.
Total.
Okay, I will repeat that. I will repeat that. 944 71 922 71.
Yes, exactly. Yes.
So Sabu, can I leave? Thank you all. Thank you.
Thank you.
Thank you, Kannan. Thank you, Kannan.
Thank you. I know it's a difficult subject. It is a technology intensive subject, but I try to pitch it very low for you to.
Yeah,
Uh,
here one of the thing, you are an electronic engineer, and we
Yeah.
are not in near same wavelength. Our wavelengths are different.
അതുകൊണ്ടാണ് ഞാൻ വേവ് ലെങ്ത് മാറ്റി പാടിയതെന്ന്.
But
മാറ്റി പാടിയത് നന്നായി. ഞാൻ ആ തുടക്കം
ഏതൊരു വ്യക്തിക്ക് മനസ്സിലാക്കാൻ പറ്റും. വളരെ കൃത്യമായിട്ട് സാറിന്റെ
തുടക്കം
base എല്ലാം clear ആയിട്ട്.
സ്റ്റാർട്ടിങ് വളരെ ഡിഫിക്കൽട്ട് ആയിരുന്നു.
കണ്ണൻ അത് മോഡുലേറ്റ് ചെയ്ത് വിട്ടു.
ശരി അപ്പോ ശരി.
In
ഗുഡ്
our
നൈറ്റ്.
wavelength.
okay, right. Good night.
Thank you, sir. Thank you once again. Thank you. Bye.
Good night all of you.
Good night.
ഓ താങ്ക് യു.
Right.